So, good morning, good evening everybody, hope you are fine and you are enjoying this course. So, as we were discussing that in the last stages of the last class was basically the concept of stochastic process in a very simple manner, the Markov process and the Markov chain and what are the implications for the stock prices. So, we are considering with repetition I am saying that whatever the prices are as of today are only dependent on the last day's price or the last moment price. So, if I am basically trying to find out the prices at intervals of 1 day, then conceptually if I do remember I had mentioned that the closing price would be taken as the price which basically predicts all the information which has been available throughout the day. So, today's closing price would basically have all the information based on which you can predict tomorrow's closing price. Then the tomorrow's closing price would basically would have all the information based on which you can predict for day after tomorrow's price and so on and so forth. So, this is only for first order, that means one step backwards. In case we are considering that today's and tomorrow's has all the effect on day after tomorrow, then it will be two step process or second order and so on and so forth. So, in a Markov process, movements in a variable depend only on where we are, not the history of how we have reached there. So, our main concern is what we are now and based on that we try to protect. So, if you consider the concept of probability theory very simply, it would mean that the probability of x t, that is of today, would depend on x t minus 1. So, this is of first order. If you are saying that rather than this, let me erase this. So, if I am saying this, which means probability of x t or whatever the random variable is, its value or price or whatever function we are trying to analyze, this would be dependent on the just immediate backward t minus 1 and back to back, which is t minus 2, which is if I draw a time scale, this is basically t minus 1, t minus 2, then t would basically depend on the first and the second. Then t minus 1 would depend on t minus 2 and t minus 3. So, you will basically go one step at a time backwards. So, Markov process for stock price is clearly consistent with the weak form of market efficiency, which asserts that it is impossible to produce consistently same level of superior returns, because the reason is very simple. If all the information is available with all the players in the market, obviously there would be demand and supply which would basically either move up or down. So, going back to the demand and supply curves. So, if the curves or the demands and the supplies moves in parallelly, obviously they are shifting depending on the pull, whether demand is more than the supply or supply is more than demand or vice versa, which is less. Based on that, you can again find out immediately the price and quantity. Now, the information would be very instantaneous, considering it's a perfect information market, because if somebody has an extra information, he would immediately make a profit, and that information of the profit would immediately emanate and go to all the players who are in the market, and everybody would start playing in that way such that demand and supply would again come back to equilibrium. So, as we were discussing, it basically consistent with the weak form market efficiency which asserts that it is impossible to produce consistently superior returns with trading rules based on the past history. In other words, we have not discussed this technical analysis, the technical analysis would not hold true. So, obviously, but if you consider the fundamental analysis just for the information, it means the general concept of what the actual characteristics of the companies are, whether we are able to understand its price to earning ratio, whether we are able to understand its market share, whether we are able to understand its profit and loss account, that is depreciation, the assets, the liabilities, that would give us much better information, and we are able to predict the prices of that particular company in a much better way. So, consider a stock price is currently at 350. At the end of 1 year, it is considered that it will have a probability distribution given by this. So, this 350 is the mean value, and this 400 would basically the variance. So, if you see, this is the nomenclature we are using. So, mean is the mean value. So, the normal distribution, this is the mean, median, mode, whatever you have, and this is basically the 2 standard deviation. So, this is 1 standard deviation, we are trying to find the square of that, which is the variance. So, n mu comma sigma square is a normal distribution with mean mu and sigma square as the variance, then we would wish to answer what is the probability distribution of the stock price at the end of, say for example 2 years, at the end of, say for example half a year, at the end of 1/4 year, and so on and so forth. So, what we are actually interested is that given the distribution at time t, we want to find out what is the distribution at time t plus delta t. That means instantaneously next moment of t, the normal distribution would have a certain mean and a certain deviation. So, standard deviation we want to basically find out given the information as it is today, considering that the simple concept of Markov process and stochastic processes really hold true for the stock prices. In Markov process, changes in successive periods are independent. This is important to remember, which means that if we have the values and we want to find the difference between these values. So, let us maintain is delta 1, delta 2, delta 3 and so on and so forth. These are the differences. Then the differences are IIDs, that means independently and identically distributed with a certain mean and a certain standard deviation, which means the variances are additive and but standard deviations are not. Thus, in our example, it is correct to say that the variance is 800 for 2 years and not the standard deviation is 40 for 2 years. So, that means given the values of the standard deviation of the variances which we had. So, 400 was basically the variances, and if 2 years down the line it will be additive. So, that means it will become 800. So, generally we will see later on that the functional relationship between the volatility and the time would be very important, which means that volatility whatever the function is, it is basically would be proportional, directly proportional to the square root of the time difference between as of now and, say for example 2 minutes down the line, 3 minutes down the line, 10 years down the line, whatever it is. But in the case of trying to find out the volatility, which is the variance for the stock market, we will follow the simple concept that the variance can be additive, which means in the long run the values of the standard deviation, the values of the volatility would basically be a function of either the square root of time or time, depending on how you are trying to implement volatility. That is important. So, whatever the function you are using to denote the volatility, that would basically dictate what is the relationship of time which is coming into the picture. So, we will consider two very simple processes based on which we will try to find out the implication and what is the actual formula for Black-Scholes model. So, first is the Wiener process. So, let us first make the perfect background for the Wiener process. Consider Z is a random variable and Z would follow a Wiener process if the following procedures or the following assumptions hold. What are those? First, the change of delta Z, that means Z are the values of the random variable. So, between each Z period or Z values, we will basically have the delta Z, which is the difference. So, say for example, Z is taking values of Z1, Z2, Z3, Z4, Z5. So, technically the differences would be Z2 minus Z1, Z3 minus Z2, Z4 minus Z3 and so on and so forth. So, we would be considering that delta Z as the difference in the values of the Z. So, this is what it says. The change delta Z during a small interval of time, delta t amount of time, would basically be related to in this way, that if delta t is the time, delta Z is the difference, then the relationship between delta t and delta Z would be given by this. That is, delta Z is equal to some epsilon multiplied by the square root of delta t. So, if you remember when we were talking about the volatility, I did mention it can be dependent on the square root of time, it can be dependent on time also. So, this is what we are trying to basically bring into the picture. And also remember that the delta, the epsilon which is here has would be a normally distributed one, which is a standard normal deviate with a mean value of 0 and a variance or a standard deviation of 1. The values of delta Z for any two different non-overlapping periods would be independent. So, if you remember the values of a random variable, the differences of them, if they are basically IID from time to time, then obviously they would have a distribution. So, this is what it is saying, that the delta Z for two different overlapping periods, there would be IID, they would basically have a type of distribution, and the relationship between time, delta time, when I am mentioning time is basically delta time, and Z, which is delta Z, is related by a standard normal deviate. So, hence if you see the actual standard normal deviate, it would mean what? Its variance would be 1. So, obviously, its variance is 1, its mean value is 0. So, if we have different values of delta t given by the concept that it is related to epsilon and delta t, then in the long run the expected value of z is 0 and the variance of delta z would be delta t. So, here we will say z follows a Markov process. So, if you look at the values and you are basically trying to find out delta z here, then it will be going like this. Now, if you take a snapshot here, then in the long run the mean value of z, which is expected value of del z, which is this one, is 0, which is fine. And if we look at the variance, so variance would be at different point of time. So, if you are trying to find out that the variance which is a normal distribution, considering this is normal, then it will look like this. Now, watch here, even though it is a little bit cluttered, if you see the mean value would always be 0, but if you consider the variances, they would basically keep increasing further you go down along the line. So, say for example, if you find out the differences further down the line means that how big is the differences where you are trying to basically measure the variance of delta z. So, say for example, if your time periods are this and in one other case the time periods are this, in this difference if delta t obviously is more and in this case the delta t is less, consider delta t1 and delta t2 where delta t1 is greater than delta t2, then in this region the variance of delta z would be much more than the variance of the delta z in this time period of delta t2. So, again I am repeating, given delta z are the differences of the random variables considering z has some particular distribution. So, your next question would be what is the distribution, that is what I am going to come, and I did mention delta z would have a IID considering they are non overlapping. In that case the distribution of delta t would be given by a normal distribution, but remember it would have a mean value of 0 considering the fact that epsilon has 0 mean and 1 as standard deviation, but its variance is now dependent on the time factor. And we will see later on also that the standard deviation, as I was talking about, the volatility is dependent on time depending on how you are trying to express volatility. So, now if your total time difference is the capital T. So, you have started here t is equal to 0, t is equal to capital T, and you have been able to break down into small delta t's and consider the number of such divisions are n, which means the total time difference would be n into delta t. Now, in that case the expected value at time t is equal to 0 was 0, it will continue to remain that, which means the difference in the expected value of z and 0 would be 0, which is this one. And if we consider the variance is exploding because it is dependent on time t. So, if you consider the variance difference between when you started off the z process at time t is equal to 0 and time t is equal to capital T would basically be t, which means the whole process would be expanding in such a way that it basically moves out where the mean value remains as it is considering this is true and the variance expands given the fact that it is dependent on time t. So, here I am basically considering the Wiener process. I am trying to basically have a microscope and zoom down in more in order to understand how it looks. So, if you see the drift, you have t not delta t along the values. I think I did not mention one thing properly. Yes, let me come back to the slide. Here you are measuring t or some concept of t along the x axis, and here you are measuring delta z or z. So, this is sorry I just missed it. So, remember that along the y axis we will be measuring delta z and z, some function of z, and along the x axis you will be measuring t delta t or some function of time. Similarly, here also t or delta t along this z or delta z. Okay, again coming back to this where we left. So, here you have the drift and you are measuring t along the x axis and z along the y axis. So, this is basically the drift. So, this is technically the average value which you have. So, if you find out the expected value would be coming out to the straight dotted lines which is parallel to the x axis. Now, what I am doing is that I am slowly now zooming in, trying to basically take a micro view, trying to understand more in details how the overall drift process considering the Wiener process fluctuates. So, if you follow the diagram just shown, the orange one and the diagram which is being shown in the blue one, that is the same thing, only I have used a different color in order to make things life easy for all of us to understand. So, if you see the orange one, it is very smooth, there is no jagged lines. So, now if I look at this and expand it, how does it look? It would look like this. That means, there are much more variations as you basically zoom in and take a micro look. So, let us again take this small view and again expand it. So, if you see as you go more into the micro level from step to step more closer, you will find out the overall variations in the actual stock prices would be happen like this, such that it will give you much better information how is it fluctuating, and the equations which we dealt would basically give you a much better theoretical knowledge how the stock markets in a very simple manner can be modeled using the simple first order stochastic process or the Markov process which we have just discussed. So, now a generalized Wiener. So, initially we have considered the Wiener process where delta z was equal to epsilon into the delta t factor whatever the functions were, and we consider epsilon was with normal distribution 0 mean and variance of 1, and based on that we found out that what was the expected value of delta z, what was the variance of delta z, what was the expected value of z capital T minus z 0, where z capital T was the value of z at time t is equal to capital T and z 0 was the value of z at time t is equal to 0. Then we also found out that what is the relationship of the variance difference, that means variance of z capital T and z 0, which means the differences of the variances. We also found out what was the relationship. Now, let us go one step forward and let us analyze the generalized Wiener process. Now, if you remember the formula, it had only epsilon and t. So, there was no other constant factors, or say for example, epsilon was a normal distribution with a fixed mean and a fixed variance. So, obviously, many questions would come up in your mind, what in place of epsilon we had another normal distribution where its mean value and standard deviation was also changing with respect to time. So, how would it happen, or say for example, rather than have epsilon into the functional form of delta t, you also have a plus addition value which is no more constant, but is changing with respect to time, or it is a constant which remains fixed with respect to time. So, if you have different models, how would we basically generalize that? This is what is the underlying fact based on which we are trying to analyze the generalized Wiener process. A generalized Wiener process would have a drift rate, that is the average change per unit time, which would be 0. The drift rate of 0 means that the expected value of z at any future time is equal to its current value. That is what we were saying when we were saying this. This is what we mean, that as it is progressing z, the value of the difference of the z values as we proceed from time to time in the long run would basically be 0. That means, there are fluctuations, but the fluctuation would basically even out and it will be along the straight line which is the x axis. The variance rate of 1, means that the variance rate of the change of z in a time interval of t equals t, which means that if you remember the functional form which we have discussed, it means that expected value would be 0, it is not dependent on time, but the concept of variance or volatility would now be dictated by time. So, we will now close here and continue our discussions of the Wiener process and the Ito's lemma and how it leads us to the concept of Black-Scholes model. Thank you.